Swayam Prabha. Digital India. Educated India.
Let us continue our discussion on beams. See, in the last class, we had looked at when there is a variable loading on the beam, we cut two sections, one at a distance x from the origin, other one at a distance delta x from it. So, we have looked at two sections cut on the beam and we have isolated this and have drawn the free body diagram for this. So far you have seen that in general both shear force and bending moment varies from point to point along the length of the beam. They do not remain constant. When they remain constant, they are exceptional situations. We had seen when shear force is constant, we had also seen situation where bending moment is constant. They are special situations. In general, both shear force and bending moment varies along the length of the beam. So, when I have taken sections at x and x plus delta x, I will have to write the shear force and bending moment on the negative surface and positive surface with an incremental change. You have to recognize when we wrote the sign convention, for convenience we had shown a finite length. I said it is showing what is happening on the positive surface and what is happening on the negative surface. For convenience, you have provided a distance between them. It is not a block taken out from the beam. Whereas here we cut at section x and section x plus delta x, and you have to write the incremental change in the shear force as well as the incremental change in the bending moment. And it is easy to get the equations of equilibrium written. And what we have learnt was a very important interrelationship, dV by dx equal to minus Wx. Please note, we have got this expression when loading is acting downwards. We have got the expression for that situation. And we have also been able to look at the moment equilibrium and finally got the interrelationship dm by dx equal to v. See, I have all along been saying it is a good habit to plot loading diagram, shear force diagram and bending moment diagram one below the other. In fact, you would see the advantage in the problem that we are going to solve next. You know, I have a bookshelf, impromptu bookshelf. You have a plank and you have two supports and books are stacked on top of it. You know, I also thought that I should give some simple exercises on how engineers do idealization. And you know very well that books have different weights and they are stacked on top of it. Suppose you want to find out what is the bending moment acting on the plank, what can be an idealization to start with? Can I take the weight of all these books to act at the center of the beam and start proceeding, or can I do slightly better, yet simple to analyze? Can I have an idealization? What What are the idealizations you have seen in terms of loading? When I said that you have to accommodate the weight of the beam in civil engineering constructions, how do they model the weight? As a uniformly distributed load. So, as a first approximation, you can also replace this by an uniformly distributed load on the beam. Can we do that? Reasonable approximation. You are not putting the entire weight on the center of the beam, you have taken one step ahead. If you want to analyze it as such, you may have to bring in the weight of each one of the books, what is the length it occupies, and put the variation. But finally, it can be averaged out to an uniform loading like this. It is a good approximation to start with. See, the question here is, determine the optimal position of the supports. So, you have to understand how do I impose the condition of optimality. When do you say the supports are located at optimal positions? You know very well that bending moment is going to vary along the length of the beam. And do you realize by adjusting the supports, you can modify the variation of bending moment on the length of the beam? Can I put the supports at the ends of the plank? Will that be an optimal position? Obviously, that is not an optimal position. Intuitively, can you say what should be the length A? Because we all say, why don't you solve by intuition? What is the ballpark figure? What do you feel? Intuitively, what do you feel? L by 2. Now, let us go and look at the mathematics and find out whether our intuition is correct. For the idealized loading, the moment I idealize the problem, I do not worry about the actual problem. The answers will closely match with reality with a small amount of error, which is tolerable for a given design situation. Intuitively, you feel that A should be equal to 0.5 L. We will see what way the mathematics is going to give us the answers. You have just taken some blocks and then put it below the plank. Suppose you want to keep your table clean and you have stacks of work, you have found out a plank and then put a plank and then put some support. And what way can I idealize this support? I can simply say it arrests translation in the vertical direction. You can freely move the plank on top of it. So, I can simply say that this is replaced by a normal force. You get the idea how engineers start looking at problem, capture the essence of the problem, but simplify from mathematical analysis point of view. And we have also seen earlier, for the purpose of finding out the reaction, I can replace the distributed load by its resultant. And this is a problem involving symmetry. You should recognize that once I find out A y, B y is automatically fixed. Even before solving, you can guess what is the answer, what is A y and B y. They support the load W L. So, it should be 1/2 of W L. So, I have sigma F I equal to 0. This gives me A y plus B y equal to W L. And I have also told you, when we solve problems, when we write moment, when I put the subscript denotes about which point I take the moment. So, I take the moment about point A. So, that gives me, this gives a clockwise moment and this gives an anti-clockwise moment about A. So, I have minus W L A divided by 2 plus B by A equal to 0, and this gives me A y equal to B y equal to W L by 2. In fact, when you solve problems after problems, even by inspection, you should be able to identify what should be the values for AY and BY. Nevertheless, you should write down the mathematical expressions to convince the teacher that you have really determined them, not copied it from anybody else. Now, you have a problem like this, and I have to find out the variation of shear force and bending moment along the length of the beam. You should know how many imaginary sections that I have to cut, so that I get the variation for the entire length. That is also the decision that you have to take. See, if you look at here, when I move along this length, I have a load coming across here. Suppose I have this support at the end and this support at the end, just one cut was sufficient. We have solved a problem which is simply supported, uniformly varying load. We just had one imaginary section that determined the variation along the length of the beam. So, one aspect which you have to keep in mind is, whenever you have external loads, you have one section like this, and between these two supports I need to have one section, and after this I need to have another section for this. Or you can also argue from symmetry, if I determine for a section here and section here, you can also write without calculation what should happen for the other section. But I would do for all the three sections. So, one of the decisions that you have to take when you have to draw the shear force and bending moment along the length of the beam, you should have a clear idea how many imaginary sections you need to take it, so that you get the expression for the entire length of the beam. So, I put a section at x and I identify this as a section 1, and this is easy for me to analyze. So, I take out this, and we are following the convention by Merriam. So, I put it on the positive surface, a negative direction V is positive and anti-clockwise moment is positive. But the moment I put these forces as per the sign convention, I will have to put all my quantities with respect to the reference axis when we employ the equations of statics. Do not make a mistake there. So, I get V as minus Wx. I am not solving it step by step, I am missing steps. I expect you to fill in the blanks. So, when I use m equal to 0, that gives me m equal to minus Wx squared divided by 2. So, then I move on to a section in between the supports A and B. So, I have a section like this. I take out this, draw the free body diagram, make a neat sketch of the free body, label all these values. See, if you had numbers for A, W and L, the arithmetic will look simpler, but now this is written in a generic fashion. So, it looks clumsy in that sense, and I have to complete the free body. So, I put the unknown forces, shear force and bending moment like this, and when I apply the equations of statics, I get the shear force as WL by 2 minus Wx, and I get my moment equation as WL by 2 multiplied by x minus L minus A divided by 2 minus Wx squared by 2. Please verify this mathematics. Check in your notes, in your notebooks, verify the calculation. So, I have determined for this portion, the portion 1, what is the expression for shear force and bending moment, and in between the supports I had made a cut and I determined the shear force as well as bending moment, and I would also make a cut at this portion of the beam and write down the equations. So, I would take a section like this, and this is what I said, you have a freedom to choose which portion of the imaginary cut you will take it for finding out the forces. In the earlier two cases, we had taken the segment 1 for analysis. In this, the mathematics is lot simpler if I analyze the segment 2. So, this is where your sign convention is important to get consistent results, including sign for plotting shear force and bending moment. And I would put the shear force and bending moment. I am looking at the negative surface. On the negative surface, we have said the positive V is considered as positive, and we have taken the bending moment as clockwise. And this is again very easy to analyze. I get the shear force as W into L minus X, and I get the moment variation as minus W by 2 L minus X whole square. See, what I need to do is, I need to plot the variation of shear force and bending moment along the length of the beam. So, I need to get the values at key points. Which form the key points? Definitely the starting point of the beam is important. Whenever I have a load change, I would like to know what is the value here. I would also like to know what is the value here. I would also like to know what is the value at the end. In addition, I would also like to know what is the value at the mid span of the beam. See, for shear force, the expressions are simple and you can easily write down these values from the general expression. In order for me to easily plot the variation of bending moment, let me get these values of bending moment from the earlier expressions. We have already determined for the section ending at A generic expression for moment as minus W x squared divided by 2. So, if I need to find out what happens at point A is located as x equal to L minus A divided by 2. When I substitute for x in this expression, this simplifies to, please do the simplification yourself. I will give a minute for you to do the simplification, and you can verify your simplified expression with what I have in my slide. So, you have to go back to your notes and see what was the original expression we had for the segment ending at A, for the segment between A and B, for the segment after B. And you have symmetry in this problem. So, what I would get for segment 0 to A would be similar for B to the end of the beam. We would see that black and white in our slide, fine. So, when I substitute for x, this expression turns out to be m equal to minus W divided by 8 into L minus A whole square. Can you find out what is the value of the bending moment at mid span of the beam? You have the expression, you have the generic expression at mid span x equal to L by 2. So, substitute x equal to L by 2 and calculate at the mid span what is the value of the bending moment. Before even I do that, I find out what is the moment at B, where x is defined as x equal to L plus A divided by 2, and because of symmetry I get an identical answer. I get an identical answer at A and B, that is what you anticipate. This is what I say, you should have physical appreciation of the problem. When there is symmetry, the results what you get also show that symmetry. So, that is one kind of check while you solve the problem whether you are on the right track or not. And if I have to find out the bending moment at x equal to L by 2, I will have to substitute x equal to L by 2 in this expression. The generic expression is W L by 2 multiplied by x minus L minus A divided by 2 minus W x squared by 2. When I substitute x equal to L by 2, I am going to give the final simplified expression. Please verify whether you have also got m equal to W L A divided by 4 minus W L squared divided by 8. Some of you seem to have got identical answer. Now, we are all set to plot the variation of shear force and bending moment along the length of the beam. And what is shown here is, I am also giving you ideas how you should plan your notes and answer scripts. We have done all the calculations earlier and the final expressions are written down here to facilitate easy plotting of the shear force and bending moment diagram. So, if you follow that discipline, it will help you. Now, I will plot the shear force, and mind you, this animation is plotted from left to right. We will revisit this again, why I plot from left to right, because I have also told you, you have to isolate the free body, determine the forces acting at various sections of the beam, fine, but you should also have another methodology to verify whether your final answers are correct. For that, if I move from left to right, it is easy for me to plot the shear force when I use the convention of Merriam. So, I have this expression, this is V equal to minus Wx and it varies linearly, and once I have a external support, the shear force increases at that point and the total value is equal to WL by 2, and then it drops down, touches 0 at mid span and goes like this and plotted like this. Please mind you, this is only illustrative, it is a highly exaggerated picture of the shear force variation. You do not get confused that I plot shear force very clearly, I also plot the bending moment, they are of different units also. Shear force is a force, so I write it in terms of newtons. When I go to moment, I write it in terms of Newton meters. You should not conclude, in my picture I have a very large shear force and it is going to introduce me large stress. In fact, in a practical problem, usually the maximum stress developed by a shear stress would be at least 15 to 20 times less than the bending moment. The stresses induced by bending moments are very significant and that truly dictates the design of a beam. Shear is only an additional effect that you have to consider. So, when I have to find out optimal support, I must look for what is the variation in bending moment to take a decision. Shear force is only an intermediate step, and since you are learning how to draw shear force diagram and bending moment diagram, we are also drawing the shear force diagram for this problem as well as bending moment diagram for this problem. So, you have to keep in mind, from stress analysis point of view, the effect of bending moment is very significant on the beam. The stresses introduced are much higher than the stresses that is caused by the shear force. So, do not get carried away by an illustrative sketch. Now, let me plot the bending moment variation. I have the expressions here. See, this shows that this is a quadratic expression. This is also a quadratic expression, and this is also a quadratic expression. And let me plot, we have already determined the values at key positions. What would be the bending moment at the starting point? At the free end, it is 0. So, you have that what is happening at support A, what is happening at midspan, what is happening at support B, and what is the other free end. All these quantities you have. And let me plot this. I have the bending moment diagram drawn like this. The bending moment diagram is very colorful, and this is again illustrative. See, do not compare the peak magnitude of bending moment with peak magnitude of shear force. They are shown very clearly to identify what are the variation. They are not plotted to a scale. Now, the question is, you have drawn the diagram so nicely, you should also investigate, have you drawn it correctly? Is it a correct bending moment diagram? We have definitely followed. This is the quadratic curve, this is the quadratic curve, this is also a quadratic curve. You have learnt few slides back what is the interrelationship between the bending moment and shear force. Can you use that knowledge and verify whether this bending moment diagram is correct? It should be, if you want to accept as a final answer, it should verify the test, it should pass that test when you investigate whether the interrelationship what we have evaluated is valid here. Shall we go and investigate now? I have drawn consistently in all my slides the sign convention for shear force and sign convention for bending moment. See, I deliberately put it at different places. If you see always on the right side, then you do not get the idea of what is a positive surface and negative surface clearly. So, when I write this as a block, if I have the outward normal in the positive direction, that is the positive surface. If I have my outward normal in the negative direction, it is the negative surface. And we have looked at two expressions. One is dV by dx equal to minus Wx. And what I get this is the slope is negative. That is what it says. And obviously, yes, I have the slope of this diagram is, this is a negative slope. So, the shear force diagram, there are no major hiccups. Shear force diagram is consistent with whatever the interrelationship that we have got. Let us look at the interrelationship between bending moment and shear force. The slope of the bending moment diagram is related to the magnitude of V. V is positive as well as negative, fine. So, I will have to look at the slope and verify am I on the right track. I have put a slope here, and what is this slope here? This is a negative slope. Does it tally with what is given in the V? V is negative, so this slope is valid, that is also fine. And as I come to the center of the beam, what happens to V? V goes to 0. And suppose I plot a tangent at the midspan, I would also have a 0 slope. So, this parabola is quite alright with the sign convention and also the interrelationship that what we have determined. So, there is no major hiccup in this parabola. Let us look at, have we drawn this segment correctly? Can anybody identify whether this segment is also correct? It can also be correct. It can also be correct. I have not said it is wrong. We have to establish why it is wrong if we say that it is wrong. Let me again draw the slope. I draw the slope here. My shear force is positive here. My slope is also positive. Apparently, it looks I am not on the wrong side. But look at one more aspect, when it on the free end shear force is 0. What I am getting here? I am getting a finite slope at the free end. It cannot be there. See, suppose you have a plotter where you feed in this equation, because people have become very lazy now. You know, you have symbolic computations have come, no visualization, you simply feed in the expression, it itself plots beautifully. If you have that luxury, then you will not make a mistake in plotting the either the shear force diagram or the bending moment diagram along the length of the beam, because you do not have to apply your mind. You are going to determine the various y coordinates based on the x coordinate, you can easily plot and connect it, you will not make a mistake there. There is a possibility of making a mistake when you do by hand calculation, and when you have this, you have another clue that slope is 0 here. Suppose I replot this portion of the beam, does it satisfy all of it what we have learnt earlier? This is again a parabola, second degree curve. Here again the slope is positive, tallies with this, but the important clue what I have used is, I have identified a point where the slope is 0, that guides me in finding out whether I should plot the curve like this or in the opposite way. You can also think in one more direction. See, I can also draw a straight line and find out what is the value at the midspan. I can easily find out that is just the average, fine. And you can decide whether the average from your expression at the midpoint, not the average, the actual value at the midpoint is higher than this average or lower than this average. That will tell you whether I should plot the curve in this fashion or in this fashion. So, now do you realize when I say that you have to plot the loading diagram, shear force diagram and bending moment diagram one below the other, at least prompts you to think and find out whether your answer is correct, whether you have drawn these variations correctly, translated your expression correctly in the drawing. So, that is very, very important. So, that is the reason why I want you to plot one below the other, and I have also given these for a numerical value of A equal to 0.63 L, and I get these numbers like this. So, this shows how the variation is. I have done it for two cases. I have taken a case where A is greater than L by 2, and I have also taken a case A is less than L by 2. Just to illustrate, by changing the position of the supports, you can have totally a different variation of bending moment along the length of the beam. The bending moment variation is totally different here. You can see this in the previous slide, it is like this, and mind you that these are not plotted to scale. I am only interested in the variation. In this case, bending moment is both negative as well as positive. In the other case, bending moment remains negative for the entire length of the beam. And I go back to the generic solution which is given in terms of A. Now, we have to go back and answer the question, what is the optimal position? The intuition said it is 0.5. We have to verify whether it is 0.5. How do I put the condition? See, if I have to apply the optimal condition, I must also know how to bring in that in mathematics. Along the length of the beam, the bending moment varies from negative to positive, and one case when I brought them very close, I had that as on the negative side completely. So, by placing the support, I can vary the variation of bending moment along the length of the beam. Can I say that I would determine these supports in such a manner that whatever is the maximum negative bending moment is equal to the maximum positive bending moment. That means, you are limiting the magnitude of maximum bending moment possible on the beam. Even at the start of this discussion, I said we are not really worried about the sign of the bending moment. I will provide you a reason from strength of materials a little while later. We will revisit it again. Do you get the idea? If I have to get the optimal position, even though you have not done a second level course, I have always been saying this is only feeding information to your second level course, and I thought, can't we not have one problem where with your knowledge you can also do some optimization and get an optimal solution. So, from that perspective, this is a very nice problem. So, what we are really trying to say is, if I find out length A such that the bending moment in the negative side and positive side are equal, let me put that condition. So, when I equate these two expressions, I get my A as 0.586 L. You can argue either way. My intuition was correct, I have got 0.5. I can also argue you are not correct, you have got 0.586. This debate can continue for any length of time. Okay. But what you will have to appreciate is, when I have a beam, suppose I have the bending moment is in one direction, I am having this as clockwise bending moment, and when I see the resistance offered by the beam, it is tensile on the top and compression at the bottom, and mind you, the maximum tensile magnitude and maximum compression magnitude are identical, fine. And when I reverse the moment direction, the top fiber gets compressed and bottom fiber gets elongated. So, this is the reason why I said, when I want to find out the bending moment, I am more interested in getting the magnitude along the length of the beam. Either way, the member is going to experience similar loading, either on the top fiber or the bottom fiber is going to experience a similar loading. So, this also gives you a convincing answer that for optimal condition, you equate the maximum negative moment to maximum positive bending moment, so that you find out a position where the maximum magnitude is minimized. So, that is what we have done. The next problem is, draw the shear force diagram and bending moment diagram for the cantilever beam with a triangularly varying load as shown in the picture. See, this is one of the common variation of load that you come across in engineering application. The other common variation what we usually come across is uniformly distributed load. Usually, when you are analyzing beams in civil engineering, the self height is so important, you cannot ignore that. That is modeled as uniformly distributed load. Another load that you come across very commonly is the triangular loading. One example is, when I have a fluid which is exerting pressure, that could be modeled as a triangularly varying load. And here again, to plot the shear force and bending moment diagram, take a section at x, isolate it. Since you have complete knowledge of what happens in a triangle, you know how to find out the centroid as well as the area. One can easily find out the resultant, and that acts at the centroid, which is at a distance x by 3 from the base. And using this, one can apply the equations of statics, and sigma Fi equal to 0 gives me the value of V as minus W x squared by 2L. This is the first occasion that you come across that V varies as a quadratic expression. All along you have seen V remaining constant or varying as a linear load, whereas here, because the loading itself is varying linearly, I get a quadratic expression for V and a cubic expression for M. M equal to minus W x cube by 6L. One can plot using these expressions, but we will also see, suppose I have the load variation not as a triangular, but it is given in a very generic fashion. What is the kind of mathematics that I will have to use? Here again I take out this and write it in a general fashion, and within this load variation I have another variable delta, and go from fundamentals how to find out the centroid. There again you use a similar expressions, same thing is mimicked here. So, I find out what is the resultant force and the moment because of this loading from first principles. So, that is what is written down here, the free body diagram is written down, and the function W as a function of delta is written as W delta by L, and sigma Fi equal to 0 gives me, when delta goes to 0, I get this as an integration, and this finally gives me V equal to minus W x squared by 2L, and MB plus integral 0 to x, this is nothing but W delta divided by L multiplied by x minus delta d delta equal to 0. This gives me bending moment as minus W x cube by 6L, and one can plot the variation along the length of the beam. So, you plot this is a quadratic curve, and you plot this you have to take it as a cubic curve. While doing hand plotting, it is very difficult to show a subtle difference between a quadratic curve and a cubic curve. Definitely you can draw it and show distinctly that it is not a straight line, and we can also verify whether the interrelationships are satisfied. I have dV by dx equal to minus W. So, the slope is negative, and when I plot the slope is negative. So, this is okay, and when I look at the plotting of bending moment diagram, the interrelationship is dm by dx equal to V, and V is negative. So, I expect the slope to be negative. So, that gives a verification that we are on the right track, and to plot the curve whether this way or the other way, it is better that you find out what happens at the center. You can imagine a straight line and find out the average and find out what is the value, and from the expression for bending moment find out the value at the center. Compare these two values, that will guide you whether to plot the curve in this fashion or the opposite fashion. We have so far seen a variety of problems where the focus was how to handle an external load. The focus was not on repeatedly learning different problems so that you hit one problem for you to answer the question in the final exam. More on a conceptual level we have looked at it, and it is not difficult for us to complicate the whole development of loading. You can have multiple loading on a beam. I have a distributed loading, I have a concentrated moment, I have concentrated loads acting on it, and also I have a overhung beam, and you can also find out what is the shear force and bending moment variation on the beam. And when I have this, you will have to know how many sections I have to take. So, I have to take one section here, I have to take another section here, I have to take another section here, another section here, another section here. So, in all I will have 1, 2, 3, 4, 5 sections. Is it all right? 5 sections I have to do it. So, I have to do the calculation 5 times. Then only I will be able to get enough quantities for me to plot the variation of shear force and bending moment. and if I have to draw any one of this, my first step is to find out the reactions. I have to get the reactions. Without the reactions, I will not be in a position to do this computation. But you know how to handle a distributed load, how to handle a concentrated bending moment. Individually, we have solved the problems. So, when they come in an actual beam, it is not difficult for you to accommodate that in your calculation. I would appreciate you do this as a homework and bring it out, then we will have a discussion. I would expect you to identify different free bodies, put the quantities the way we have learnt in the class, and determine the values and plot the shear force and bending moment diagram. Okay. And for you to compare and facilitate your answers, I have put the reactions, and the reactions are 46.16 kilonewton on this end and 2.84 kilonewton on this end. So, it is not at all difficult for you to draw the shear force and bending moment diagram when multiple loads are given in a beam. The only difference is it is going to take you a little more time for you to accomplish this. So, in this class we have determined what is the optimal position of supports for a simple problem of arranging a books on a plank. In the process, we learned the sign of the bending moment is not of that concern, only the magnitude is very important. That knowledge you derive from what you see in strength of materials, and we have used that as a criteria to write the optimal condition and determine the distance between the supports. In a sense, it tallied very closely to our intuition, but from a Puritan point of view, it is not exactly intuition. You need the elaborate theory of bending of beams is necessary for you to identify an optimal location correctly. So, that is another way of looking at it. And in all this shear force and bending moment diagram, I re-emphasized what is the role of interrelationships. How do you interpret the interrelationships to verify your final plotting of shear force diagram and bending moment diagram. See, the focus here is, it is not that you have got an answer and you have plotted it in one way without verifying whether this is the correct way of plotting or not. As engineers, you have to be very definitive in your final answers and statements. So, you need to use every possible auxiliary method to verify your answers, at least whether it is in the range of your expectations. Some such visualization is very essential for you to become a good engineer. And we have also looked at another problem where there is a triangular load variation. And finally, we looked up a beam with multiple loadings for you to find out the shear force variation and bending moment. I want you to do it the way that we have done in the class, and in my review, I will solve it from a different perspective, at least give you an idea how to verify your answers. Thank you.